Yeah, very good morning once again. Let's start going into the details of the most important subject for your semester, which we have already said, the design and analysis of algorithm. Once again, I repeat what last time I have said is that we are going to focus on certain important aspects during our programming. From algorithmic analysis, the design is important, and analysis indirectly means complexity, and complexity, or I'll say analysis directly means complexity analysis is important, and complexity indirectly means efficiency is also to be considered carefully. But for us, we are from industry viewpoint, especially taking view of the IT industry also, requirements, we are going to focus on not only the analysis and efficiency aspects, we are never going to compromise on modularity. We are never going to compromise on readability. And we are also going to take good care of doing structured programming. Of course, we are not going to violate the efficiency at all, and we are not going to have any compromise in the efficiency at all. But for improving efficiency slightly, or for reducing some execution time slightly, we are not going to compromise on the rest. So this is our thumb rule. We are going to ensure no violation of the efficiency will be done, but efficiency will never be targeted to be improved by compromising on above. And it is possible that you can still maintain the same efficiency without compromising above. So going further, last time I have already told you that we are going to go through the insertion sort. Well, insertion sort, I'm sure some of you remember well, and those who were more sincere students, they must have revised insertion sort before coming to the class. Well, if you have revised, great. If you have not, still, I'll say insertion sort is effectively that how do you initially adjust your cards, playing card, or how do you initially, I will say, keep the cards in your hands, keep the playing cards in your hands. How do you position them? That is more or less closer to what we are going to discuss. Yeah, if you remember, say, if you are being given 10 cards, you got initially, let's say, one card of 5, then you got, say, a card of 8, then you got a card of number 9, or let's say number 10. Now, say these cards are in your hands. Let's assume now you get a new card with number 3. What do you do? If you are playing card, it's a normal tendency to keep the cards in the sorted order in your hands. And indirectly, what you do is, this was initially the 4th card in your hand. You pick up the card, keep it on the right side of your hand. In the rightmost corner, you will place it. And then you will find, okay, is it supposed to be before 4, 10? Is it supposed to be even before that? Is it supposed to be even before that? And then you will find, yeah, I needed it somewhere here. But if it is going to be a kind of an array, so effectively it will mean that you have to create a space here. That will mean, first of all, when you know that you are supposed to keep a 4 number card before 10, so you will shift 10 to the next position and have an empty space here. Then you will shift 8 to this position and have another empty space. Then you know that, okay, 5 is still bigger than 4. So 4 is supposed to be even on the left side. So you will bring 5th to the second place. And now your first place is empty. So you will put your 4 here. So initially you had 3 cards already corrected, and 4th card which you wanted to place this, let me say that the new card was 3. So this is 3 to be placed. So you compared 3 with 10, 3 with 8, 3 with 5, accordingly shifted, and finally card with this now. So all 4 cards in your hand. Now let's say you get next card to come is say 7. Again, effectively, initially you will put 7 at the last position, and you have in your hand all these 5 cards. But then you will see, okay, 10 is bigger than 7. So you would like that 7 has to come on the left side. So you will probably require a place to be created in an array. Then comes 8. 8 again says that yes, 8 is also going to be bigger than 7. So you will bring the 8 to the next position here. 5 coming to this position. And then after this 5, comparison of a 7 versus a 5 will mean now the 7's position is correct, available. So you will place a 7 here. 3 and 5 will remain undisturbed. More or less, this is what is insertion sort. If you take care of doing this over an array, the only difference being that in case of cards being played in your hand, you simply go and make a place, and then in your hands, you will have the card inserted at the correct position. So effectively, insertion sort simply says that it's a one-line logic. Although again, we are not supposed to go into the design aspect of this, but just to revise for you insertion sort, it says at a time, say you have to every time say insert the new value into the already sorted, or I'll say insert this into the already sorted list at the correct position. Insert at the correct position. So effectively, it means that I have an array, I have a list. Let's assume up to this is a sorted. Of course, this will become after certain steps. So I say up to this, let's say it's a sorted. I am talking of element J. This is a part of unsorted list. So out of unsorted list, I will say the first element of unsorted list, or I'll say 1 to something, say that is J minus 1, is a sorted list. And then you have jth element onwards as unsorted list up to, let's say, n. So I will say jth element is to be inserted, in the sorted list. Sorted means A1 to J minus 1. You have to insert this element into this sorted list. And how to insert? Of course, that will mean that 1 to J minus 1 elements are here. I'll say 1 to J minus 1 elements are at this position. This value will be compared from the backwards, and accordingly position will be created and insertion will be done. So that is one liner for this. In detail, I will say that if I have to implement insertion sort, you have already done that implementation. I'm not going to repeat the whole process. Let's directly start writing the code. So I will say, let's say I'm supposed to have, let's assume that my elements are on total 1 to n, currently unsorted. Although we can take 0 to n minus 1 also, but just 1 to n will make some of the analysis easier, remembering easier. So I'm doing it from 1 to n. And I will say, so for j equal to 2 onwards, I will start. Initially, I can say A1 itself can be considered as a sorted list. So I can easily say A1 to 1 is guaranteed sorted, and A2 to n is unsorted. So I have to do this process repeatedly. Of course, at a time, one element will be sorted and added, one element will be inserted. So sorted list will keep on appending. And finally, we will keep on adding one more till we have done everything. So obviously, I will say j from 2 up to j n, I have to repeat. This means effectively, I'm saying j aj to be inserted where in at correct position into a 1 to j minus 1, or you can easily say this. So effectively, now I have to write the logic for this. When I write the logic for this, this is exactly what is called as a design aspect. So I decided design step 1 that I have to do this for n number of times or n minus 1 number of times. And then I will say design step 2. I have to decide the logic for the other one. When I am able to write this also with all loops and control statements, and then all corresponding logics more or less is verified to be correct, I will say, yes, the code will be ready, design will be ready. So this is what we call as a design of the solution. For the time being, I am not going to go in more detail of design. As we already know, insertion sort we have already implemented in the last semester. So I will say, fine, let's go into the coding part. So I say for j equal to 2, j less than equal to n, j plus plus, and I have to insert element. Which element is to be inserted? I will say k. Let's find out the key. Aj is to be inserted. Now, if I have to insert aj, obviously, I can say it is to be inserted up to last position backwards. So I will take a variable I starting from j minus 1. That means whatever list is already sorted, 1 to I is sorted, and this element is to be inserted. So I is obviously j minus 1. Now, I have to compare this value, first of all, with this, and keep on doing in the backward. Backward means I have to have some loop, but it's not going to be exactly I times loop, because in between, if the place is found, I will not require further I to go downwards. So instead of using for loop, it will be good to use a while loop. While condition, we will decide what to write. But ultimately, what I want to say is that I am going to do copying of this value to this place. And why this place? This place is already key has this value copied. So this place is free. This element can be shifted and it will not lead to any loss. For example, I have the values 5, 7, 10, and now the element coming is, let's say, 3. So key is at present 3. So this 3 in the array can be overwritten. So what I will do is I will compare 3 with this. So I will have accordingly the condition written here. But that means if the while loop repeats, if the while loop is entered, 10 should be copied to this position. That will effectively mean A of I plus 1 will be copied the previous value. And of course, for the next loop, I should be reduced, I minus minus. Now, based on that, how long should I continue? So let's decide how long I have to continue. First, that I might not have this. Now, if I am habitual of doing indentation, you can see I saw that these two statements are needed to be part of the same while loop. Immediately when I wrote and I forgot braces, I will recall that yes, braces have been forgot. I have a habit of writing this indented code. You can see automatically that habit continues, and that helps me in knowing that I'm probably missing some logical mistake or some logical syntax or some logical statement which I have to put like braces here. Now, one case can be that in this case, ultimately, 3 will never be a situation which forces me to stop, because as long as 3 is a smaller, I will keep on shifting. And then ultimately, once I reach here, I know that there is nothing more to compare. So a point will come where comparison will not be possible. That means while I is greater than 1, I can definitely compare. When I am reaching to 1, that time, whether I have to do this or not, I have to see. So when I is 1, value is not shifted. That means, say I reach to A15, that time also comparison will be needed. So ideally, I can say this should be I greater than 0. This is how it will be decided. But I need not go to that situation. Another situation can be there. So I can say one condition is I greater than 0. And what? Let's say if this value was 12, 12 meant no copying read it. So if the key value is greater or equal to than the current AI, I will not require a shifting. Means if a key is correspondingly less than AI, I require to copy back. As long as this condition is true, the values shifting will be needed. Ultimately, I might reach to the start of the array where no more data exists. I reached to the starting index. Remember, I said my array is 1 to n, and that means A1 is the first element. So A1 is the first element. Then if I am comparing with the first element, after that, no comparison will be needed. So I can easily see this should be more or less correct. Now I have to find out where the key has to be placed. So if I think carefully, obviously it will be something in terms of I. Now whether this is I or this is I minus 1 or this is I plus 1, I have to think of and accordingly write. So if I think carefully without wasting much time, I can say it will be needed AI plus 1. This process to be repeated, and I can say this is my total logic. Now, knowing this, I will say once I have written this code, first thing will be the correctness of this code should be verified. So for the correctness, there is a concept of a loop invariant, which is explained in the book of a core man. So last class, I forgot to tell you that the book to be used is the Introduction to Algorithms. Introduction to Algorithms. 3rd edition, Algorithms. 3rd edition, and the publisher is a PHL. So this is one of the one of the most commonly used book, and the author is Corman, and many more. So it is known as a book by Corman, and you must be happy to know that the book we are referring is none other than it's a professor from MIT. So MIT professor USA's book you will be studying, and you should be proud that yes, you will be reading to that book. And it is the world's most popular book, and across world, every university follows this book as a textbook. So read this book. In that book, there is a concept of loop invariant given. Must read from the book. I am not going to go in detail of that at present, but you should read it and complete that proof also. Sometimes later we will discuss how this loop invariant is decided, how it is used, etc., etc. But just continuing for the analysis part, let's reach to the analysis component. So now we do see what do we mean by analysis. So analysis effectively means I should be able to find out how much time it will take for the execution, time of execution. But you could say the time of execution I can calculate by noting the time on the computer and then ending time of the computer. Well, that can be one way, but primarily it will take few milliseconds or few nanoseconds, or few milliseconds, few microseconds, or few nanoseconds, hardly noticeable. Secondly, if you talk of execution time, your typing time, your input giving time, all that will also come, display time, all that will also come. And not only that, at that time, your OS could be busy with some other works. And during that time, that extra time will also get contributed to this. It's like in between, OS becomes busy with some printing activity and sends some data to the printer. During that, it will not respond, or you are copying data to a hard disk, secondary disk, it gets busy there, it won't work. Accordingly, all that will happen. So execution time, actual execution time is not a good solution. Actual execution time we cannot use for analysis aspects. Secondly, CPU to CPU, RAM to RAM, and other properties, hardware, speed, all those will also matter if you talk of actual execution time. So all these are also computer dependent, PC dependent, and we cannot use these for the analysis. So this doesn't become a good solution. We think of doing a better solution for analysis, that let's try to count step count, number of statements and how many times those statements will execute. So if I assume that various different statements are there, how many times each statement executed, can I find summation of these and different statements execution steps or execution count? If I can know, then I will say assume some execution time of each statement, execution time for each statement as a constant. For each statement, we will assume as some constant C1, C2, C3, etc. Knowing the count or frequency, I will say C1 into frequency of first statement or steps of first statement plus C2 into frequency or count of how many times the second statement was used, C3 into F3, like this. This will give me overall total count, overall total steps or total statements. And then this becomes a better indicator because it is independent of hardware or the other behavioral issues. Independent of hardware and the user behavior. I say assume it for this. What does that mean? User behavior, I mean typing time, etc., not considered. Secondly, I will consider n to be very large. Very large means maybe 50,000, maybe 1 lakh, maybe more than that. Why? This will mean few extra simple lines won't make much difference. So even if I have written 4 or 5 extra lines in the coding, which are not repeated, few extra lines won't matter if they are not part of loops. If they are not loops, etc., extra few lines, when I'm talking of n to be very large, total steps will become 50,000 into something, 50,000 into 50,000 into something. If they are not loops, etc., they will help me in ignoring certain minor issues. We will be more clear once I talk of this discussion. But before that, I say, then computer uses this as a RAM model. RAM model means it's not random access memory. So it is effectively something similar to that, but it is not RAM memory which you are talking. I'm saying this model says that it's again going to be the similar process of having single CPU. So no parallelism, no parallel execution possible. So I say it is effectively going to be a RAM model, and I am going to use no parallel execution. And I'm going to have, sorry, I'm going to accordingly use in this case no other input or system characteristics to come into picture. To come into picture. Just 1 second. Let me just pause. Just 1 second. Let me. Yeah. So just I was having a glass of water, and so I said we are not going to have this any other characteristics coming into picture. That will effectively mean that RAM says it's a random access machine having no hardware characteristics to come into picture and no parallel execution to be there. So these two aspects collectively are assumed a characteristics of the corresponding random access machine that is called as a RAM model. Now, based on that, we are going to do the analysis, means just try to have the step count. For that, let's see whatever code we have written, insertion sort code we have written. So I'll quickly write that code and then analysis will become easier. Say, I say statement number 1 is for I is for j equal to 2, j less than equal to n, j plus plus. Then I had statement number 2. Within this, I said, say here itself, I will write I equal to j minus 1. Then third statement number 3 is I had a while loop. So I'll just correct this. While some condition. Then I have fourth statement where I said, say, ai plus 1 equal to ai. And then fifth statement, I minus minus. And maybe I'll just close at sixth line, doesn't count much. Seventh line, I said I plus 1 equal to key. Of course, before that, let's say I have put here key also equal to I. or aj minus 1, whatever. So this could have been taken as line number 3 also, doesn't matter. Fine. So not a big issue at all. Knowing this, now I say execution time taken on average will be, let's say, C1 for this statement, say C2 for this statement, C3 for this. I assume some constant, C4 for this, C5 for this, C6 for this. You can easily see the time taken for I minus minus could be probably much lesser than time taken for a for loop execution or for a while loop execution. So C5 could be much lesser than C3 or than C1. Similarly, I equal to j minus 1 plus key equal to ai. These are two statements. So C2 could be almost double of a C5. So those kind of things can be taken whenever we are doing the actual calculation, but still it will give me a fairly good idea how do we do analysis. Now, the most important step, I have to actually count how many times this statement will execute. Can you tell me how many times this statement will execute in terms of n? In terms of n. Later we will assume n to be very large, but in terms of n, what will be the value? Yes, you could say n minus 1 times. Almost correct, but to be precise, it's not n minus 1. Yes, I'm saying it's not n minus 1. Ideally speaking, it is n, because n minus 1 times the loop works correctly. Loop works, but nth time you will be going, checking the condition. So this condition will be checked and this statement gets executed nth time. It will be obviously false and then you will come out of the loop. But this statement executes n times. Yes, now you can say because loop executes n minus 1 times, this statement, both statements will execute n minus 1 times. What about this statement? Not sure, because this is a while loop. And I have a condition while I greater than 0 and something. Now, worst case, it can execute maybe n minus 1 times. Best case, it could execute only once. 0 will never happen because condition will be checked. So I assume, let's assume this statement executes aj time for variable, for j being for j. And j we have, because for every j this will be executed, I can say j being a 2 to n. When j is a 2, I say it executed a2 times. What can be the a2? We will see. Then similarly, I will say when j is a 3, corresponding to that, it might execute some a3 times, and accordingly we will see. In total, I am saying, considering every value of a j, in total, this statement executes these many times. I'm not saying that inside the loop it will execute a2 times. I'm saying I have totaled all a2, a3, an. So I said totally this executes these many times. Like this, I said total this executes this total executes n minus 1 times. So whatever time loop executes, accordingly this has been decided. Outer loop executes, then this will decide this loop to execute. Accordingly, how many times this will execute. Let's say if loop executes a2 times, then I say first time j was 2. If loop executes a2 times, this statement executes a2 minus 1 time. Next time, I have a3 times loop executing. That will also execute, this statement will execute a3 minus 1 times. Effectively meaning that I can easily say this is nothing but j equal to 2 to n, but this becomes aj minus 1 times. Across all values of a j, similarly, this will also have the same thing. J equal to 2 to n minus 1 aj minus 1 times. What about this statement? So this statement will execute for every jth loop once. This loop executes this loop inside went n minus 1 times. So this statement executes n minus 1 times. Total count, I can easily see, is nothing but C1 multiplied by n plus C2 multiplied by n minus 1, maybe into, if I say there was other statement also, so I will say this was plus, similarly C2.2, first statement, I guess this was one statement and another also. So then accordingly, I could say C2.2 into n minus 1. That is for, let's say, this is separate statement. So this is being statement I equal to j minus 1. This being key equal to ai, which I forgot to give a separate line number. So I am just writing there. Plus summation of, or I'll say C3 into summation of j equal to 2 to n aj plus C4 into summation of j equal to 2 to n minus 1, 2 to n. And this will become aj minus 1. aj minus 1, not minus here. And so and so. Similarly, plus C5 into something, plus C6 into n minus 1. Now this becomes problem to be solved. Of course, I need to know aj. So aj is not fixed. Had aj been fixed, the values were clearly calculatable. Had aj been fixed, had aj been known, total count was known. So, but now I can easily see aj is data dependent. So once aj becomes a data dependent, I say such situation leads to cases which I call as a best case, worst case, and then accordingly I take average case. For example, in this case, best case means aj to be minimum. Best case doesn't mean that data has data, I will say always sorted is best case, data always not sorted is best case, or reverse sorted is best case. No. Best case means the variable which was repeating should get the minimum value. What can be the minimum value? aj can be minimum. That means while loop doesn't execute at all. I don't go inside the while loop at all. That will mean aj should be 1 every time. That will mean I will just go to the while loop, check the condition, and find it is false and come out. Means that best case will mean that your time complexity, which we just calculated, was C1n plus C2 into 2 on average, let's say, into n minus 1. Two statements I have taken both collectively here, plus C3 into summation 2 to n and aj. aj is 1 plus C4 into 0 effectively. C5 into 0 because aj minus 1 will be 0 plus C6 into n minus 1. That will be equivalently C1n plus 2 C2n minus or minus 1 plus C3 into n minus 1 plus C6 into n minus 1. Ultimately, this will become some linear equation of n. I can say it will be nothing but an plus minus b. Even I can write an plus b, where b can be negative also, but I can easily say some constants multiplied with n plus something. When I say so, this becomes one best case time complexity. Out of this, I will say, because dominating term n being very large will always become being very large, then dominating term will be primarily a n, and constant also won't matter much whether a is a 3 or 5 or 7, because n is 50,000, 60,000, 20,000, 1 lakh. So I can say yes, that is going to be the more or less indicator of time complexity. So it will be loosely called as O n. We will not represent A, we will not represent B, because we are more willing to know rate or order of growth. So analysis primarily focuses to know growth order or rate of growth, and rate of growth is dependent on in a linear way on n. That is what we conclude in this case. Yes, it can have 50 extra statements, doesn't matter when I'm talking of n to be 1 lakh. Order of growth, if I am saying n 1 lakh means it will have certain 1 lakh into some, say a is 5, so 5 lakh. But n becomes a 10 lakh, straight away it will become 10 times. So growth of the order, order or rate of the growth is directly dependent how n grows, then I say order of n. On the other hand, talk of worst case. Worst case will mean, what should be the worst case? Aj to be maximum every time. What can be the maximum value? Just think of that. What can be the maximum value? Say j equal to 2. What should be the aj as a maximum? Aj maximum will mean, if you remember, the condition was while I greater than 0 and ai plus 1, or not ai plus 1, I'll say ai. If the ai value is greater than key or key less than ai, something like that we wrote, and I will be accordingly going for this change. So what can be the maximum times loop repeat? Maximum time will mean we will come out of this. If we come out of this because of this loop stops due to this, that will be the only reason to stop, and that will be the worst case. If you remember, I was j minus 1. So that means from j minus 1 up to 1, it will go, and at j equal to 0, it will stop. So when I becomes 0, it will stop. So that means if j was 2, I was 1. For I equal to 1 also, it will execute. I equal to 0, stop. It took 2 executions for while loop. Other case, when I was 2, I equal to 2 also it will execute. I equal to 1 also it will execute. I equal to 0, I will say stop. But while statement will execute 3 times. So effectively, my aj becomes equal to j in worst case. Yes, if in worst case, that will mean, now if I say is this case, let's go back to the previous analysis, and I can easily see that in this analysis, if I replace aj as j, I can do the calculations. So now I will say this will mean C1 into n plus C2 into 2n minus 1 plus C3 into j equal to 2 to n, this becoming j, plus similarly C4 into whatever you have done. Try to solve that. Obviously, you can easily see this will come out to be a quadratic equation. I'll leave it to you to find out what will be the exact quadratic equation. I can easily say it will become an square plus minus bn plus minus c. Although plus minus is also not compulsory, we can write plus, but I simply say that yes, it can be some negative also. Now, if this is the answer, I will say we will claim this to be order of n square. Why order of n square? Again, order or rate is what we are interested to find out or compute. Rate of growth. And dominating term which decides this. So dominating term without constant is what we look at. Without constant. And big O says, forget about the constant. So this big O notation gives the reasons why constants are ignored. But dominating term in this case is n square, because if n is 1 lakh or n is 10 lakh, so n square will mean 10 raised to 12. When something grows or some steps take 10 raised to 12 steps, then any step which is taken 10 raised to 6 times will be much lesser than 10 raised to 12 based steps. So any extra steps, 5, 10, 20, 50 taken, plus some steps taken 10 raised to 6 steps, plus some 100 steps extra. But this side is going to be 10 raised to 12 steps. If n was 10 raised to 6. If n was 10 raised to 6, this will be 10 raised to 12. This will be something 10 raised to 6. C being, let's say, 100, 200, 300, whatever. So overall, I can easily say, let me just save and have one extra slide so that we can just wind up, because my slides are getting over. Yeah, just let me continue now. So now I can easily see that overall, when I said an square plus bn plus 6, if n is 10 raised to 6, I will say it will become a into 10 raised to 12 plus b into 10 raised to 6 plus c plus minus c, whatever you say. So whatever be the value of b and c, 5, 10, 20, 100, these values are much lesser than a 10 raised to 12. So this becomes the dominating term, the rate and growth dependent on 10 raised to 12. So I say big O complexity primarily targets to know how many steps or how many growth orders will be there. Of course, A, if it is 10, and in one other case, if A is 1 by 10, that makes a difference. So big O is not the best solution to compare, to have exact idea, but target of analysis is to compare algorithms with the different time complexities. With the different time complexities will be comparable with the different time complexity. So if any algo has, say algo 1 has time complexity of a big O of n square, algo 2 has time complexity of, let's say, big O of n, I can guaranteedly claim that ON is better. Because whatever constants bigger could be, I can guaranteedly say algo 2 will be better. But if algo 1 has O of n square, algo 2 also has O of n square, then I cannot say both are same. No, both might not be exactly same. Both are not exactly same because they have only order of growth same. It is still possible that algo 1 could have been, say, 1 by 10, or I'll say not 1 by 10, let's say simply, I'll say it was n square minus 100 and minus 200. Algo 2 could have been 300 n square plus 400 n plus 600. Both will still mean same time complexity. So same time complexity just says order of growth is same, still one could be faster than the other or slower than the other. But primary focus is to find out overall growth wise if any algorithm can be claimed to be superior or inferior to other. That is the target. With this, we will be stopping. I will leave to you to calculate the average case also. Average case of insertion sort will mean that on average, it is neither best or not worst every time. What will be the time complexity? On average means, let's assume not best, not worst. So I will say on average, assume say j by 2. Earlier I said best case meant j every time execution once. Worst case meant j times. So I say aj you can consider to be equal to j by 2. So for average case, take aj as j by 2 and then try to calculate the time complexity, and then you will be able to find out what is average case time complexity. So this is how time complexity analysis is done. Similar will be the process for space complexity also, but with new algorithms, we will keep on explaining and it will become more and more clear. So next class, we are going to talk about another algorithm, which is merge sort. You have already done that. Again, I will not focus on the design part now at all. I'm going to directly talk of merge sort analysis component and understand better how analysis is done. But merge sort has two variants. First variant is what you have done earlier in data structures, Horowitz and Sahni book. If you have studied in that book, you might have studied. And another is given in the Corman book. So I will say the second version is given in the Corman also. Both are very similar with a minor difference. Just go through that and we will discuss in the coming class both of these and then do the analysis. Of course, both are within the scope of the same discussion, so not a big issue. Stop.